Okay, good morning. Almost at the end of 201. We have plenty of time left. So we're going to introduce the topic of AC power today. That's the last remaining topic, last chapter for our class. Next week, we'll look at the example problems. And then from that point out until the end of at the end of the last week of classes, we'll just do in-class activities, refresh, go over, problems, homework, whatever the students want to do. Okay. We've done 7 quizzes so far. We'll do quiz number 8 on Tuesday. Monday is a holiday, so Tuesday and Wednesday we'll meet again. And Tuesday will be quiz number 8. That'll be based on chapter 6, filter circuits. And then quiz number 9, that is the Monday of Monday of finals week, be based on AC power. It'll be big, it'll be long. The reason is I will not assess AC power again on the final exam. Okay, so quiz 9 will be the only time we will, assess that. So we'll do it today, then we'll do one example on Monday, another example on Wednesday, and then assess it on Monday, and that's it. Done. Okay. All right, so let's bring up the class notebook and begin AC power. I labeled it as yes. No, I will, we'll push it back to until after the example is covered. So all through the quarter, usually if the topic is not covered, I always, push the homework back until the example problems are covered in class. This is also the topic for lab 8, those of you who are taking the labs. Okay, so power in AC circuits, the label says 5.5. Well, it's because the book that we use has it as part of chapter 5. Okay. All right. So electrical power is typically transmitted over long distances. At some point in your lifetime, you would have noticed these kind of structures, right? I obviously, growing up, we have seen these, but a few years ago, I was parking outside of Sprouts, that store that had just opened in Madonna Plaza, and I parked and I opened the door, and I almost missed hitting a concrete structure. So I go out and it's like, what is this structure in the middle? And then I look up and I see this huge tall tower, transmission line tower. It's right in the middle of the parking lot outside of Sprouts. And so you have this long distance transmission lines coming all the way from south, from the plant, going all the way north to all the surrounding areas, going over the mountains, going tens of miles, and in some instances in life, it's hundreds of miles long. Okay, so electrical power is typically transmitted over very long distances. This will be a very critical point in the topic that we are about to discuss. Okay, long distances could mean tens of miles, tens to hundreds of miles long. And of course, the power, we always talk in terms of a circuit which has a source connected to it and then the load. In this case, the source is located at the utility company. The utility company, which would have a power plant somewhere, is the source that is providing the energy to the customers. The customers will have the loads. In this case, the distance between the source and the load is tens or hundreds of miles long. Okay. Now, customers are of two kinds, residential and commercial. Okay. Commercial or industrial customers have inductive loads typically. They have huge inductive loads that run constantly. In some cases, they might be running 24/7, right? You have an industrial warehouse or a factory. You have these electric machines that are constantly running. These electric machines have coils. These coils are electrically represented as inductors. So industrial customers have hundreds of thousands of such machines running all the time. All of those put together is one huge inductive load. Residential customers, not so much. Residential customers, the biggest load they would have is basically your HVAC unit, your heating and cooling system, and then your washers, dryers, refrigerator, the compressor in the refrigerator perhaps, and that's about it. And if you think about it, washer and dryer with the biggest load, how often do you run it? maybe once a week, twice a week, perhaps, an hour or less, right? So as a large load over an average period of, like, let's say a month, it's negligible, it's nothing. Whereas an industrial customer has huge inductive loads that run 24/7 in some cases, right? It's constantly spinning, constantly going. The machinery is always churning. So what do we know of inductors and capacitors? We studied voltages, currents, and power for resistors in chapters 1 and 2. We studied the voltages and currents for inductors and capacitors in chapter 3. We looked at the energy transfer phase in chapter 4. And in chapter 5, we introduced the topic of AC voltages and AC currents. And we talked about how an inductor and capacitor, because it has reactance and energy storage capabilities, the energy flows in and out constantly, right? For an inductor, the energy flows in the positive half cycle, and the energy flows out of the inductor in the negative half cycle. For a capacitor, it's the exact opposite. Energy flows in the negative half cycle and flows out in the positive half cycle. So when you have a industrial customer for a utility company, you'll have huge inductive loads that are running 24/7. Means these are inductors that require constant energy. And because these loads are inductors, the energy is constantly traveling back and forth from the utility company to the industrial customer over long distances. Okay, so if you are an industrial customer and you are a utility company, these distances could be hundreds of miles long. If not hundreds, at least tens of miles long, right? At least tens of miles long. So inductive loads, what do we know about inductors? They're energy storage devices and they have reactance. They have reactance. The power associated with this reactance is known as reactive power. Okay, reactive power. So we have looked at the power associated with a resistor. That power is termed as real or average power. And that is associated with a resistor. The term real comes from the fact that the mathematical representation of this power is using the real number, real component of that complex number. Hence, it is termed as real power. I prefer to not use that term. I prefer to use average power. Okay, but as engineers, when you're studying, you should at least know if somebody talks about real power, they're talking about the power associated with a resistor. The reason I do not like it is because if it says real power, it makes it seem as if the reactive power is imaginary. And again, as I've stated before, reactance is not a figment of somebody's imagination. It is very real. It has a physical basis. It is only the mathematical representation that is imaginary. Hence, the reactive power associated with the reactance is also represented with the imaginary number. And so sometimes it is also termed as imaginary reactive power. But there is nothing imaginary about it. It has a physical basis in real life. It requires actual voltages. It requires actual current. It's only the mathematical representation that is imaginary. Okay. So again, reactive power is associated with inductor and capacitor. Okay. When you add up both real and reactive, we represent it as total power, but because we now are using real and imaginary numbers, when you add it up, the power is referred to as total complex power. Okay, total complex power. Total complex power. So far, so good? Any questions? Okay. So what happens when you have an inductive load? Power is transmitted back and forth, back and forth, back and forth from the utility company to the industrial customer, right? Now, if your source is localized, think back to lab 7 last week, or if you're not taking the lab, resonant circuits. You had an inductor, you have a capacitor, and you have a resistor in the same circuit. What happens? It's localized, very, very close, right? Maybe a few feet. Power comes from the source, goes to the inductor, positive half cycle, negative half cycle, flows out, goes back into the source. Constant exchange of energy taking place, but the transmission line is not as small. It's not localized. It's tens of miles long. Now, when you transmit over long distances, power loss becomes a very big deal. It's because resistance R is rho L over A, directly proportional to the length and inversely proportional to the cross-sectional area of that conductor. And that conductor, if it's miles long, even if you take a small 10-foot section of that conductor, its resistance might be very low, less than 5 ohms, 10 ohms perhaps. But now if the length increases to tens of miles, even hundreds of miles, think of how much resistance is in the line. The overhead transmission line would be a very, very good conductor, but even with the good conductance, if L is increased to hundreds of miles, that R resistance is increased, and so over long distances, power loss is a big deal. So think about this. If you are an industrial customer, you flip the switch, your machine turns on. And let's say we have Dr. Strange on the case. He slows down time. And you can see in the positive half cycle, the inductive load requires power. It will require both real as well as reactive power. The real power is associated with the mechanical energy. Okay, that is the one that is actually doing the mechanical work. The reactive power is associated with the reactance. It is not doing any real work. It is simply the stored energy. It is used to set up the magnetic field in that inductive motor. Okay, so in the positive half cycle, when the switch is flipped, the inductor receives all of that power. The customer receives all of that power from the utility. Some of it is used for the real portion of the work, and some of that power is used for the reactive portion. So in the positive half cycle, what was that? Sorry about that. All right, so in the positive half cycle, the energy flows into the inductor. So once the switch is flipped in the positive half cycle, the energy flows into the inductor, meaning it has traveled tens of miles long. There is some power loss that occurred along the way. But in the negative half cycle, the energy flows out of the inductor. Now it is again traveling miles away to the utility company. That's where the source is located. And again, some power loss occurs. So in only one cycle, there's a tremendous amount of power loss that is occurring. You all with me so far? Now, this positive negative half cycles occurs at least 60 times in 1 second, right? If it's a 60 hertz power line, it's a very low frequency considering everything. 60 times in 1 second is still a huge amount of power loss. So the energy transfer is taking place back and forth 60 times in 1 second. Think about how much power is being lost 24 hours a day. The machine is running 24 hours a day. Make sense, right? Transmitting back and forth 60 times in a second, 24 hours a day. Huge amount of power loss taking place. So the more you travel, meaning the more the energy travels, the more losses occur. So as travel increases, losses increase. And a big portion of that travel is needless, right? Because the reactive power is just coming back and forth. It's not doing any real work. So it's just being transmitted back and forth all the time. No real gain. There's no purpose to it. So we want to put a stop to that. And fortunately, we have a component that can do exactly that, which is the capacitor. Capacitor absorbs energy or receives the energy in the negative half cycle. Remember, capacitor, like an inductor, is also an energy storage device, but it's exactly opposite in many respects. And so this is one of those lucky aspects. Capacitor absorbs energy in the negative half cycle, and it sends it back in the positive half cycle. So instead, if you place a capacitor in your circuit right in front of that load, instead of traveling all the way back to the source, the energy is now localized. Meaning when you once first flip the switch on, utility company sends the energy to the inductor in the positive half cycle. Negative half cycle, it sends it back out. But instead of traveling all the way back to the utility company, if you place a capacitor in front of that load, it now only travels a short distance into that capacitor. In the negative half cycle, energy flows out of the inductor, goes into the capacitor. The positive half cycle, capacitor sends it back out, goes into the inductor. It bounces back and forth between the two like a ping pong ball or a tennis ball. Does that make sense? Let's take a pause. You think on all of that. Let me know if you have any questions. Yes. How is energy going? What? So as an example, let's say the inductor requires 10 units of energy, and we'll just talk in general terms, right? No voltages, currents, or power. Let's say there's one machine requires 10 units of energy, and the source, meaning the utility company, sends 10 units of energy. And let's say it sends 15 units of energy. Okay. Now, electricity is always present for us, right? Depending on how many loads we turn, meaning one half of the lights in this room are on, one half is not. If we wish the electricity is available, we can flip a switch and turn on the other 4 lights, right? So let's say the utility company is sending 15 units of energy. The industrial customer uses 10. When the switch is first flipped on, it uses 10 units of those energy. And out of those 10, let's say maybe 5 is used for the real portion, meaning average power. And then 5 units are used for the reactive power. That's when the switch is first flipped on. Now, once it receives those 10 units, if you place a capacitor in front, 5 units goes to the resistive portion, 5 units goes to the reactive portion of the inductor. If you place a capacitor in front, and we're talking about ideal system, that 5 units of reactive power coming out of the inductor goes into the capacitor. And let's say it's an ideal system, no power losses occurring during transmission. So from the next cycle onwards, instead of requiring 10, now it only requires 5 units, and the other 5 for the inductor comes from that capacitor that is stored in there. And so now the utility company is sending 15. It doesn't require 15. First time it required 10, but from that point on, it now requires only 5. Does that make sense? Does that answer your question? Okay. And if you did the lab, this was what you did in lab 7. You had an RLC circuit, and you first flip the switch on, energy flowed into the inductor. Then it flew out or came out, and it went into the capacitor. Then it came out from the capacitor, and it went into the inductor. At one particular frequency, the system was perfectly balanced. The energy from that inductor came out, went into the capacitor, and they were exactly equal. So the energy flowing out of the inductor went into the capacitor, and the requirements of the inductor were satisfied completely by the energy coming out of the capacitor. So as an example of that RLC circuit, let's say the source was sending 10 units of energy. Once we flip the switch on, the inductor received 5 units. Let's say the inductor received 3 units, capacitor received 3 units, and the resistor received 4 units. The 10 units of energy divided amongst the 3 components. 4 units across the resistor. Our output is taken across the resistor. Once the system reaches steady state, the inductor requires the 3 units of energy, but is now supplied by the capacitor. So the source is sending 10 units every cycle. The inductor requires only 3, and that is now sent by that capacitor. So the system is perfectly balanced, and the 3 units are coming and exchanged between the inductor and capacitor. The 10 units coming from the source are not absorbed by the inductor, not absorbed by the capacitor. It's completely delivered, entirely delivered to that resistor only. And that resistor now has 10 units of energy. Output across the resistor goes to a maximum, and it occurs only at one particular frequency, which is known as the resonant frequency. So whether you took the lab or you didn't take the lab, that is what happened in chapter 6 and in lab 7. The system is perfectly balanced, and because it's perfectly balanced, the energy requirements of the inductor and capacitor are confined between the two. And all of the output of the source goes to that resistor. Now, that is, of course, ideal scenario. There are other losses that occur. We are not taking those into account for now. But does that explanation make sense? We are looking at 2 different aspects of the same circuit. Yes. Yeah, but we are not looking at that. It behaves like an open circuit, but it's still, there's exchange of electrons and energy always taking place, because the faster it switches, the more the capacitor behaves like a short circuit. So there are many different aspects of analyzing a system. We can look at semiconductor physics. We can look at the chemistry. We can look at the movement of electrons in the line. We can look at impedances, which is what we did when we were looking at filters. because the application of that RLC circuit was as a filter. So we were looking at impedances and seeing how it opposed the incoming signal. But here we are looking at a different aspect. We are looking at power transmission. Here the frequency is not changing. If the frequency of the, the supply frequency 60 hertz is going to stay at 60 hertz, it's not changing. So we are not looking at that aspect. We are not looking at the filtering aspect of the system. Does that make sense? Right? So it's multiple aspects or multiple views of looking at the same topic. Okay. Resonant circuit, resonant frequency we were looking at was as an application of the circuit as a filter. That's why we're interested in using resonance. But physically speaking, that is what is happening in the circuit. Exchange of energy is taking place, and at resonant frequency, it's perfectly balanced. In real life, we can never get perfect balance. Never, ever. Okay. There are multiple reasons for why we can't. One of the simplest reasons or the common reasons is because the load of the customer as an entire load unit is never fixed. Some machines will be on, some machines not. Some machines might be running at full speed, others might be running at low speed. So it just depends on the time of day. It can vary from minute to minute, from second to second, it could change. So if our inductive load requires 10 units of energy, our capacitor is designed to supply maybe like 8.5 or 9 units of those, like 90% of those, not 100%. You can never design a system to deliver 100, because if you try to design it that way and your QL, for the inductor goes down, your capacitor might now supply 11 units of energy. So if the inductor requires 10 and your capacitor is supplying 11, now you go the opposite way. It's still pulling energy from the source because the capacitor is now absorbing more energy. Make sense? Right? So in the interest of compensating the inductive load, we now overcompensated and went on the other side. So this process of choosing a capacitor and designing the system is known as power factor correction. Power factor correction. Okay. And that is what is the topic for, lab number 8. That is next week. So let's take a pause. You think on all of that before we go to the next slide and look at equations. Let me know if you have any questions. Yes. So if I understand correctly, the question being asked is if the switch is turned off, meaning the source, the utility is disconnected from the machine, would the reactive power still keep flowing between the two? To a certain point, yes, until the power decays and goes to 0. So that is a second order circuit transient analysis. So we call it as decaying. So your power is somewhere here, and then the system decays until the response goes to 0. So energy transfer keeps taking place until it, stops and goes to 0. Yes. Most of the loads are inductor because electric machines have coils, and coil is electrically an inductor. Yeah. So every single thing that we use in residential environments, let's say Refrigerator has a compressor. Compressor has a motor, spinning motor. That is a coil, inductor. Washer and dryers have motors. Again, motors have coils, inductor. Let's see, electric oven has a heater coil. Coil has resistance. You flip on a switch. The coil opposes the flow of current and gets heated up, right? Electrical energy is being opposed, and so that coil gets hot, which we use for cooking. That's the electric oven or electric cooking range. Microwaves, again, have motors, or some, but it's a very, very small motor. So again, an inductor. Okay, so the question being asked was, are all loads modeled as inductors? The answer would be yes. Most of them are inductors. Coils are part of everyday life all around us. Okay, all right, equations. These are the first set of equations. We introduced the term reactive power. Let's begin with the real or average power. So real or average power is still represented with the letter P. That doesn't change. It still has the same units of watts. Okay. Real power P is associated with resistor. Resistor is the only device that cannot store energy. Okay. So the power associated with the resistor is termed as average power. It's called real because it's represented with the real component mathematically. But again, both powers are real. And then reactive power associated with the inductor and capacitor is noted with the letter Q. You simply pick the next letter in line. So Q is associated with inductor and capacitor. Okay, reactive power Q is associated with the inductor and capacitor, and the units are new. These are volt, ampere, reactive. Volt, ampere, reactive. VAR. VAR. Okay. Reactive power is associated with the reactance, only with inductor and capacitor. And then you add up P and Q by using complex or the imaginary number. So hence P is termed as real and Q is termed as imaginary. So P plus JQ gives you S. We skip over R because R is fundamental to resistors, right? It's a fundamental expression, so we don't use R for anything else except resistance. So we go to the next letter, which is S, and S is the total complex power. Total complex power, S. The unit is volt ampere. Volt ampere. Okay. S is equal to P plus JQ. Again, when the utility company sends electrical power, they are simply sending voltage and current. They do not differentiate between P and Q. It's the end user that differentiates between P and Q mathematically. In real life, physically, it's all one and the same thing. You just send 10 units of energy, 100 units of energy, or whatever it is. And then at the end, when the application, certain portion is used for real power, certain portion is used for reactive power. But in real terms, it's the same current, it's the same voltage. No difference. So it's P plus Q. P plus Q gives you S. And because you're using complex numbers, still a complex quantity, and we plot this on a graph on the real and imaginary axis, we get what is known as the power triangle. P is the real power represented by the real component, so it's plotted on the x-axis or the real axis. Q is on the imaginary axis. So figure A is for an inductor, figure figure B is for a capacitor. And when you join the two together, you get a right angle triangle that represents the three sides of complex power, real power P, and reactive power Q. Okay. So you have four terms and four quantities in there. The P and Q give you the real and imaginary components of the power, and then the hypotenuse of the right angle triangle gives you the apparent power, and the phase angle that it makes gives you the phase of the complex power. You can find any of the two quantities if you have two of them. So if you have P and Q, you can find VI and theta. Or if you have VI and theta, you can find P and Q. And again, these are the sides of a right angle triangle. So from those trigonometric identities, we can obtain these equations. P is VI cosine theta and Q is VI sine theta. And I'll go back to that slide in just a minute. Okay. And then this, of course, is only for resistor. This is for inductor and capacitor. And theta is the difference between voltage and current. It is known as the power angle. So it's theta V minus theta I. It is also the same as the impedance angle that we saw at the beginning of chapter 5. Not beginning, but somewhere in the middle. Impedance angle. Okay, so I'll go back. I will go forward to this slide. Once you're done here, I'll go back to the other slide. Remember the mnemonic Eli the Iceman? Voltage for an inductor is ahead of the current by 90 degrees. So ZL, theta V minus theta I, always has an angle of plus 90. ZC will always have an angle of minus 90. And so QL will always be positive. This is QL, theta L, and PL. And this is PC, QC, and theta C. Now, in real life, I mean, theoretically speaking, there is no such thing as PL or Q or PC, because a capacitor and an inductor does not have real power. Okay, I'm just making a note right now. If you were to draw a power triangle for an inductor, this is what it would look like. But ideally, of course, an inductor would not have real power P. So QL is plus 90 and QC is minus 90. Okay, impedance for a inductor is plus, pointing straight up. So QL is also pointing straight up. QC points straight down. Remember, that's the real axis. If you go counterclockwise, it's a positive angle. If you go clockwise, it's a negative angle. So QC is pointing down, negative angle. Do you want me to go back to the equations? The equation slide? This one? Okay. All right. So what is the goal? The goal is to place a capacitor in front, right? Next to the load. Graphically, if you look at it, let's say your system requires this much P, average power. And then your inductive load requires this QL. So now if you join these two together, you get an angle that is quite large. That is if you do not add a capacitor. Capacitor points straight down. So if you add a capacitor in there to compensate, and QC compensates for QL, and now your total power requirement has shrunk. Your angle is now reduced. Right? So graphically, you can see the smaller your power angle, the better for your system. Right? Physically, what we're doing is we are placing a capacitor in front of the inductor, so the power goes back and forth between the two. The energy is transferred between the two. Mathematically and graphically, we want our total Q to be reduced, QL minus QC. QC automatically has a negative sign, a minus sign, to indicate that it's minus 90. Okay. In real life, of course, power is never negative. Voltage, current, power is never negative. We put a minus sign to balance out our equations. So a total Q is QL minus QC. Graphically, you can see without QC, the angle is large. With QC, the angle is very small. So what angle would be ideal? Absolutely. 0 would be ideal. And we use a term called power factor to describe that. So ideal power factor would be cosine of 0. And cosine of 0 would be 1. That is the highest possible value. Right? Because if the capacitor is supplying more, then the angle just becomes negative. You again start at 1, 2, 3, 4, but minus 1, minus 2, minus 3. This is known as the power factor. Cosine of the power angle, cos theta, is also known as the power factor and is also represented as a percentage. Highest value is 100%. In real life, the utility company will say, you need to get your power factor up to a certain level before I can even begin supplying energy to you. Okay. Obviously, it's not possible to get 100%, right? Because you overcompensate and your requirements go down. Now the capacitor is pulling more energy. So you don't want to get into that, right? We don't want to overcompensate and go on the other side. We only want to get it to a certain level. So as an example, let's say a utility company has like 10 machines. Each one of those machines requires 10 units of energy. And 5 units of those energy goes to the resistive portion, the average portion of the power, and 5 units for every machine goes into the reactive power. Okay. Now, if they do not compensate for the reactive power at all, they would require 100 units of energy all the time, 10 times 10. The utility company has hundreds of customers. They are not set up to deliver this kind of power needlessly. It'll be insanely expensive to do that. Utility company will say, we can supply you only, let's say, with 40 units of energy maximum. We cannot go beyond that, or maybe 50, 60 units of energy. We can't supply you 100 units. Okay. So they will say, once you first, let's say there's a blackout, everything is off. When you first flip the switch on, you turn on one machine at a time. The first machine is turned on. Utility company sends 10 units of energy. After the first cycle, it only requires 5. Right? 5 goes to the resistive portion, 5 goes to the reactive portion. Then you turn on the second machine. Second machine pulls in 10. So 5 from the first machine, 10 for the second one. So it's 15. After the second machine reaches steady state, it only requires 5 itself. So total from first and second is only 10 units, and then so on and so forth. So when the power goes out, the utility company, the industrial customer has to work with the utility company to create a staggered turn on. You cannot flip all the switches on all at once and expect the utility company to supply power. The utility company will tell the customer saying, hey, you need to get your power factor up to a certain level before we even send you any more. Otherwise, we are not going to send you anything. In real life, that power factor level is around 90% or so. And this is just a wild guess for now. In PG&E, as a customer, probably work with the customer. We'll tell them, hey, your power factor is like 60% or 70%. You need to get it up to like 90%. Otherwise, we won't send you. We'll cut your power off. If power goes out on campus, campus is huge. It has machinery that runs 24/7. Central plant, the heating, the boilers, they run nonstop. Okay, there's also other systems that run nonstop. So when power goes out on campus, facilities, the managers, they have plans in place. They have to contact PG&E, the utility companies, and they have to create a staggered turn on, one building, one machine at a time. Okay. Otherwise, the campus, the company cannot send all of that power. Okay. Let's take a pause. Let me know if you have any questions. Any questions at all? Okay, let me cover the rest of the equations. So power factor is also stated as lagging or leading. And what we are talking about here is the relative position of the current with reference to the voltage. So voltage is the reference, and we state the position of the current with reference to the voltage. If current lags the voltage, we say power factor is lagging. If current leads the voltage, we say power factor is leading. And this happens for only specific components. Current lags the voltage in an inductor, and current leads the voltage in a capacitor. So if a customer states, I have a lagging power factor of 0.5, it means it's an inductive load and power factor is 50%. Theta is cos inverse or R cos of 0.5. That's what it means. The hypotenuse of the power triangle is the magnitude of S. S, again, rectangular coordinates is P plus JQ. You convert it to polar coordinates, you get magnitude, and you get phase, the power angle. The magnitude of S is termed as apparent power. It is simply the product of the voltage and the current. V times I, VRMS times IRMS. And the unit is volt ampere. It's a magnitude of S. So if S is volt ampere, then magnitude of S is also the same volt ampere. Equations from chapter 1. Power is voltage times current, and V voltage is equal to IR, Ohm's law. We had equations. P is I squared times R. P is also V squared over R. The equations will using new quantities, but the structure is exactly the same. Real power P associated with resistor R is still I squared times R or V squared over R. Reactive power associated with inductor and capacitor is Q is equal to I squared times X, the reactance, or V squared over X. As an example, this Q described for inductor would be IL RMS square, sorry, I'm out of time, times XL, and QC in terms of its current would be IC RMS square times XC. That's one more thing is this equation. S is also equal to half VI asterisk, where V and I are both phasors. And the asterisk notes that it is the complex conjugate of the current. This is just general knowledge, not general knowledge, but engineering knowledge. Asterisk means it's a complex conjugate. Complex conjugate means you are flipping the imaginary portion around the real axis. A plus JB simply becomes A minus JB and vice versa, or R with an angle of theta is R with the angle of minus theta. That comes from math, complex math. Okay, so half VI asterisk is also another equation for total complex power in the complex numbers. So we'll end class here today. I'll bid you all a good weekend. I will see you all on Tuesday, quiz number 8. If you have any questions, I'll be in my office later this afternoon.